A great pleasure to have Professor Zhiwei Yun from MIT speaking about Soergel functors, a survey of recent results.
Thank you for the invitation. So I want to talk about some general techniques for zorgo functors and applications. Zorgo functors are functors from certain sheaf certain kind of, let me say, geometric representation categories. Usually these are sheaf categories on certain varieties. And in all the examples I have encountered, these categories are in fact module categories for the certain affine Hecke category, certain Hecke categories. So some examples. And then zorgo functors will turn these will map to certain more combinatorial categories, such as most well-known example is mapped to bimodules over certain polynomial algebra. This was the zorgo bimodules. That's the name for the essential image of this functor when you work with Hecke category. And sometimes it's just not bimodule, just R modules. Sometimes it's slightly more complicated than just a copy of polynomial algebra. We'll see examples. And the key property of these sort of functor is that it is fully faithful on certain class of objects. So there are two flavors of zorgo functors. One kind is fully faithful on IC sheets. So this means fully faithful means when I talk about homes between two IC sheets, I take the graded vector space of their X groups. And likewise, the target is also graded modules, and fully faithful refers to the whole graded module. And another flavor is zorgo functors are fully faithful on projective objects or tilting objects. So these two kinds of zorgo functors have opposite geometric origin. Talk about both of them. So zorgo made the kind of pioneering observations for both flavors of zorgo functors. So let's review what happens for usual category O or Hecke category. So this means let me first talk about a version which is not a monoidal category. So I look at sheaves on the flag variety equivariant under the unipotent radical. So this just means constant along Schubert cells. Let's just call it. And the first kind of Soergel functor is just taking cohomology. Goes to weighted modules. This in a sheaf, you take its homology, it becomes from the module over the homology of the underlying space. So graded modules. It's the first kind, and this has the property that for any two perverse sheaves or semi-simple perverse sheaves, but more generally, you can take direct sums of shifts of them, namely the semi-simple complexes. That the graded vector space of X, these two sheaves, goes to graded Hom of global sections as graded modules over the cohomology of the flag variety. Right. So this is actually a bijection calculated in the Dhillon category. So this direction is a much more general theorem. So it says that there's nothing specific about the flag variety here, as long as you have a nice torus action on a projective variety, and you consider sheaves that are constant along the Birula strata. There are certain mild conditions. This similar statement holds. Here we are looking at the maximal torus acting on the flag variety left. Okay, so this is the first kind of Soergel functor. Second kind, we can restrict to perverse sheaves. The heart of the perversity structure, it turns out to be the exact functor. B goes to a priori, this goes to vector spaces. So let's just first talk about this inversion. So there are these two ways of looking at this functor. First, there is a distinguished object here called big tilting. So Roman Bezrukavnikov notation. Big tilting object inside this abelian category. So this is, this itself has several characterizations. First, it is the projective cover of the skyscraper sheaf at the point stratum. skyscraper unit set. This projective cover taken inside this abelian category. So this, by definition, is a projective object. It is also a tilting object. So this is a indecomposable extension from the constant sheath on the open orbit. So tilting extension means you extend from this constant sheath to a perverse sheath, let's say on the whole flag manifold. And you have to make sure that when you restrict and co-restrict to each stratum, you always get perverse sheaths. So both in degree minus of the length. It's a perverse degree for that Schubert cell. That's the meaning of tilting. And there's up to isomorphism a unique tilting object that has full support, starting with the constant sheath on the open orbit. So in this one example, you will see the stalk here, and both the stalk and so both the stalk and co-stalk is one-dimensional in the perverse degree. So in degree, sorry, you start with the perverse degree here. And both the stalk and co-stalk are one-dimensional, but put in degree 0 at this point strap. So that's the big tilting object. So using this object, we can describe this functor as co-represented by this one. This is performed inside that abelian category. And because it's a projective object, this is a exact functor on this category. Another description, which is from which it's also clear it will be an exact functor. This V can be interpreted as a micro stalk functor. So if we look at the so for each stratum, in particular for this point stratum, so this is my flag manifold, point stratum here, and so this is the cotangent. Okay, so this is X odd. This is identified with important radical of B. Tangent fiber here. So for any general vector here, so take some covector. So take generic C. We have the microstalk. So this again, this will be an exact functor on perverse sheaves. What it does is you take the definition of this operation is you take a local function. Let's just work analytically. Small neighborhood of x0. and take a function whose differential at x0 is your covector. And it has to be generic enough. So let's ignore those technical conditions. And then you take the vanishing cycles of your sheaf with respect to this function. So first restrict to this open neighborhood point, take vanishing cycles, and then just look at what happens at x0. In fact, that's the in fact, you can by choosing this function properly, you can guarantee that this vanishing cycle is already concentrated there. Either take the stalk here or just take the global section of the vanishing cycles. So what it measures is how much your sheaf jumps in when you slice your manifold by this function. So you have this point here. This function will give you level sets. So these are 0, epsilon, and okay, so this is our U, is some small neighborhood of x0. And what this measures is you look at the global sections of your sheaf along each slice. And then you cross this f equals 0, measures how much this global section changes. General fact about reverse sheaves that this measurement gives you an exact functor, as long as this thing is generic. So here it turns out this microstalk gives you an isomorphic functor as this we defined it by coming from looking object. Both definitions, same functor, and the key property of this V functor is well, if I take P1, P2 are both projectives. And okay, so let me, I need to introduce one more thing. A here. So here I only talked about this functor valued in plane vector spaces. In fact, from the first definition, this functor naturally upgrades to modules over endomorphism ring of this co-representing object, despite tautology. So it turns out this object is isomorphic to this co-invariant algebra. Up to, well, there's some duality on the torus, the algebra of the torus, fitting form to identify T2. Up to that, this is just forget the grading here. You get the same ring. But in particular, this is a quotient of the polynomial algebra on the algebra on the carton. But this is from the first point of view. We see actually upgrades to A modules. The second point of view also upgraded. From the second point of view, this category, first of all, secretly has is linear over. So there's tautological statement. Any category is linear over its center. So it's endomorphism again. But here, there's a bunch of endomorphisms. So this means compatible collection of endomorphisms for each object, dealing with all the morphisms. But from the definition, and see some endomorphisms of the identity functor from geometric origin. So some of these are given by the monodromy under the left translation by the torus. So every Schubert cell is automatically stable under T. Every simple perverse sheaf is automatically T equivariant, but not every perverse sheaf is T equivariant. And there's a measurement of how far away a perverse sheaf is from being T equivariant. But any perverse sheaf, there is actually a canonical action of this algebra, which is metric algebra of the carton, the algebra of T. So this will act. This will act through some power of the augmentation ideal. So action. So H action is nilpotent. So I have already secretly taken the logarithm of the monodromy. So the general setting, we should say fundamental group of the group algebra of the fundamental group acting. But here the action is automatically unipotent, and you can turn it into an action of this symmetric algebra, or even its, because this is acting nilpotently, even its completion augmentation idea. So there's some kind of a hidden symmetry. This gives in fact, that this gives all elements in the center of this category. So again, tautologically, the functor from this category can be upgraded. So any functor from any abelian category can be upgraded to module over its center. And here, in particular, we can upgrade it to this guy. That's the second version. It turns out that this any module you get from this functor automatically factors through that A, this co-invariant algebra. We in fact get the same upgrading. But once you sort of compare the two definitions, this is. So let's just take this V as valued in A modules. And the statement is that it's fully faithful on projective objects. first statement. And the second statement is if you take two tilting sheets. It's the same statement holds. So these are kind of original versions of the zorgo functor. So what can we do with when after we have these functors? So the second version allows us to describe this abelian category straightforward way. Basically, this is Artinian in category whose reducible objects are indexed by these Schubert cells. So again, by tautology, this is equivalent to modules over the endomorphism ring of all the projective objects added up. That's the general fact about Artinian categories. But Zorgo's functor gives us another way of calculating this big ring. This is the same now as the endomorphisms over this algebra A of B of so this is where we used so I should say this, by the way, these are called Zorgo's structure theorems. He called it originally, and that calculation here for the Zorgo's endomorphism theorem. Okay, so the point is, this is much easier to calculate. So let's it's not so clear at this point, but well, first of all, this A is a familiar ring. Okay, it's co-invariant algebra ring. Now the point is, these A modules, they can be calculated in an inductive way. So starting with okay, so maybe it's easier to do it for the other Zorgo functor, but the story is parallel. Okay, so this is what you can do with the second kind of Zorgo functor. With the first kind, well, we don't have a statement on the level of abelian categories, but on the level of the whole derived category. After we prove some formality statement, one can show that this derived category is equivalent to the DG. Well, it can be upgraded to a DG category, and this DG category is DG modules over a similar algebra. So this is a graded algebra with a zero differential. So that part involves formality argument. And then, as in here, we use the first zorgo functor to calculate X algebra. So it becomes graded home over this covariant algebra of global sections of IC sheets. Calculate these. For general W all the Lusztig combinatorics is about kind of calculation. So it's hard to calculate in general, but each Schubert Schubert variety has a Bott-Samuelson resolution. It's easier to calculate. Okay, so what is this? This is the section called homology of Schubert variety. And use a reduced expression of W that gives this sequence of simple reflection is called W underline. That gives you a Bott-Samuelson variety. This is yes. Successive convolution of simplest kind of objects in the Hecke category, supported on these minimal parabolics. So that's a resolution of singularities. And by the decomposition theorem, we know IC sheet ICW is a direct summand of push forward here. So its global sections is a direct summand of global sections of this, which is the cohomology of the Bott-Samuelson variety. And this is a successive P1 vibration. And it's in fact, it can be written, it can be calculated. The best formula for this is we do the equivariant version. So if we look at a single case of simple reflection, this is a torus equivariant homology of P1. this can be R covariant homology ring point under T, E or B, doesn't matter. And this has an action of the Weil group, so it makes sense to take fixed points under this simple reflection polynomial ring. After taking a fixed point, this can be identified with the equivariant homology of maybe called LS. So this Levy subgroup of G that contains simple roots corresponding to S. So that's the general calculation of cohomology of equivariant cohomology of a reductive group. And formally, this is just point mod P times point mod P over point mod P. And that's how you see these two factors or subalgebras are really mapped to this ring because they are the two projections. And this copy is common in both. So at least you see there's a map, an isomorphism. So you iterate this calculation to get equivariant cohomology of the Bott-Samuelson variety. If I divide by B, also on the left, the formula will look like an iteration of this. So R. 1, 2. So this is what's called the Bott-Samuelson module for this of simple reflections. And addition, zorgo by module over R is just an indecomposable module. A direct sum of indecomposable summands of these Bott-Samuelson modules for any string of them. Well, you can take it to be reduced or not reduced. It doesn't really matter. For any sequence of simple reflections, you can just write down this R by module. It's always here we think of it as a graded. This in general can be written as a direct sum of indecomposable objects. Again, those then the general zorgo by modules are just direct sum of those composables. And by this decomposition theorem, we see that intersection homology of each Schubert variety is a Bott-Samuelson. So it is zorgo by module. In fact, it's an indecomposable. And then theorem zorgo is that these are exactly all the indecomposable zorgo by modules. Bijection with elements in the Weil group. So the nice thing about bimodules is they're of course much more effective for calculation. So you just need to take a long enough reduced expression, write down your Bott-Samuelson module, and try to decompose it. So on the other hand, it's smart enough to basically you can recover all the Kashdan-Lusztig combinatorics out of this simple operation. It's quite a powerful tool. There are similar kind of calculation for these V functor applied to projectives. So basically here to talk about the analog of Bott-Samuelson modules in this situation, we need so they correspond to geometric versions of translation functor. So let's yeah, so I'll get to this, but the lesson we learned from calculating the intersection cohomology of Hilbert varieties is that it's nicer to work with variant versions. In fact, this kind of full faithfulness statement can be has an equivariant version. Let me just state. I look at equivariant cohomology. From so now it's an equivariant version. So it's now graded modules over equivariant cohomology flag variety. And this functor is fully faithful and on IC sheaves. Semi-simple complexes. And the image, so this sets up, in fact, an equivalence between semi-simple complexes. Semi-simple complexes in B of mod B mod B, where let's just sort of take a naive version where the Helm spaces, this is not viewed as a triangulated category. It's just Helm spaces are the graded X groups. And then go to Zorgo bimodules. Graded Zorgo bimodules. This is an equivalence. Content. Both the full faithfulness and Zorgo's characterization of Zorgo bimodules. So these are exactly by the image of cohomology of semi-simple complex. Here Helms. It's just a graded X.
A little bit back. Yeah. It's about your notation LS.
It's Levy subgroup. So let's say this is the Levy of PS. So it has two roots, alpha S, plus minus alpha S. it's natural to ask for a version of the second kind of Zorgo functor, where which we can also talk about Zorgo by modules and BunG Seminar. I forgot to mention. So this functor has another important structure. This is a monoidal functor. So if you convolve two sheaves, the result is H. Convolve two sheaves, then take equivariant cohomology. This is the same as we take tensor product over the little copy of R. So F1, F2 are semi-simple. So that all these bimodules inside are free over either copy of R. So each variant cohomology is a bimodule. R bimodule coming from copies of R from left and right, and then tensoring over the middle copy, tensoring of bimodules. The BunG Seminar module just comes from convolution, successive convolution. There's simple. So it's natural to ask for a monoidal version of the second Soergel functor. And the answer in the context of category O by paper Yunsen and Ginsberg, namely for category O, we should switch the point of view to Harsh-Chandra bimodules. For the complex group, namely the G times G and the diagonal G. This kind of Harsh-Chandra pair. And geometrically, what it amounts to is you have to make both sides symmetric. Okay, so there are some generalized infinitesimal characters being fixed. And that means geometrically we should look at sheaves with unipotent monodromy. So this is a full subcategory. Sheaves on G mod U on U, with this full subcategory generated by, let's say, IC sheaves in the older version. But now I'm allowing various extensions between these IC sheaves or standard sheaves that can have monodromy both along the left and along the right. So for example, on a single double coset, if I take a BWB, mod U, this has a topological space. The homotopy type is the torus. And the mod out by U on both sides doesn't change topology. So this is the homotopy type still. And on this torus, I can put various local systems as long as it has unipotent monodromy. So this is like a Jordan block where as large as you like, and it's convenient to work with a version where you include this universal, the kind of universal Jordan block, or universal local system with unipotent monodrome. This is a technical point in my work with Bezrukavnikov, so we can introduce some completed version. Basically, it's just adding objects of the form universal local system, but still unipotent on each stratum. So the T itself, it's a universal local system. Its stalk is representation of I1. Universal guy is vision of the group ring I1 completed at the augmentation ID. Comes a power series ring. So this category now carries a convolution, just as no, it's in this version. This there's a notion of floating objects. So like this similar, it's called a free monodromic token. So these are objects F such that when I restrict, they are both finite Valley copies of the universal local system. And shift to this reverse degree. Okay, so I want this freeness over the power series ring. So these objects turn out to behave well under convolution. So if F1, F2 are free monodromic tokens, their convolution is also free monodromic token. This is a parallel to the statement that if I have two semi-simple complexes, then by the decomposition theorem, their convolution. So this is the B convolution. Here it's the U convolution. It's still semi-simple complex. correct sum of shifted perverse, simply perverse sheaves. Here, version for floating sheaves. Now there's upgrading of the B functor. It's completed the version of a monodromic category to so the target here will be maybe call it R prime by modules. So what is R prime? So we mentioned that this category carries tautological endomorphisms given by the monodromy, logarithm of monodromy from the left, now also from the right. So each copy of the monodromy action is exactly this ring completed at the augmentation ideal. So you can use the logarithm map to identify it with power series. So identify it with the symmetric algebra on the algebra of again completed. That's the R prime. It's a polynomial, it's a power series ring of the same dimension as this R. But there, the variables are dual to each other. So here it's generated by the functions on the sorry, the generators here are elements in the Cartan of T. Generators there are elements in the dual. Otherwise, they're similar.
Zhiwei, sorry, we usually take like a 10-minute break after.
Okay. Let me just write down the zorgo structure theorem for this one. So zorgo structure theorem upgraded to this two-sided monodromic setup. It says that this functor V is fully faithful on free monodromic. Parallel to this statement. So finishing the discussion so far is using these zorgo functors beautifully upgraded the theorem with Bezrukavnikov. It's sort of there. The main point was to work with it in three groups, but let me just state for usual. We take the mixed version of a lot of equations on this side. But for the dual group, there's a monoidal equivalence. Well, there's a slight issue here, which is you have to change the home space here a little bit. This category is linear over a power series ring. This category is linear over a polynomial ring. So there's some mismatch there. You have to slightly modify your Helm space here to go back to the polynomial. Although I definitely need objects here that are free monodromic. There's such a monoidal equivalence that maps IC sheaves to free monodromic tilting sheaves, indexed also by W. Particular constant sheaf, so constant sheaf shifted in perverse degree, matches the big tilting sheaf. So this W is the same W. For the longest element W, here at the constant sheaf, here we get the big tilting. It's the free monodromic version of the C. So in particular, the endomorphism ring, so because this is an equivalence of categories, endomorphisms of this free monodromic big tilting is the same as equivariant homology ring. So one, and also the construction, from the construction, it's clear that the zorgo functors on both sides are intertwined. So the zorgo functor H tilde on the left-hand side that's intertwined with the V tilde on the right-hand side. The technical remark is that it's necessary to pass to the mixed version. This equivalence is not given by geometric procedure because, okay, although it is an equivalence of triangulated categories, but if you make a Tate twist here version, and this Tate twist will correspond to not Tate twist here. Shift in a twist will correspond to a Tate twist. Maybe it's a negative, but I can't remember. So the equivalence is really going through combinatorial objects of zorgo bimodules. Because of this kind of mismatch of Tate twists, you cannot be defined using some kind of geometric kernel. Okay, so this is a very old story. Duality paper. So I'm going to give some more recent variants of similar idea. So the plan is recent developments. So basically, these are certain techniques of constructing zorgo functors in different contexts and proving the zorgo structure theorem in them. So in the equivariant, so variants of this equivariant zorgo functor, I want to briefly talk about well, maybe just one. About Lusztig, where instead of G mod B, we fix some local system on the torus and consider strictly monodromic sheaves back to a local system on both sides. And variant of V There is a variant again with this local system, and there I want to talk about affine case variant, which is more interesting, and which is already in the work with Bezrukavnikov, because that works for any smoothie group. And another interesting variant is the situation where we look at the real points of a real reductive group acting on the flag manifold or G mod U. With Lusztig, this is Ionov. So let's first look at this strict monodromic situation. So this L is a local system on T, rank 1 local system. So that's by homomorphism. You can think of it. Think of it in this way. It naturally identifies this datum, the point in the dual torus. But you can think either way. So this gives alpha. So what do we mean by sheaf that's equivariant with respect to this L? Naively, it means suppose I have a T acting on X. The usual equivariance says the pullback by the action map. The action maps are given isomorphism. This kind of twisted equivariance just means certain L, a T factor. And then you will need a cycle relation. But here the property of L that makes this work is that there's any rank 1 local system on the torus, and so we are working over C, let's say. So any rank 1 local system satisfies this character sheaf condition, allows you to formulate the next compactor. Okay, so now we can consider this kind of equivariance on both sides. Of course, when you set up the equivariant derived category, it's not enough to just look at to give such an isomorphism. You have to look at the whole simplicial resolution of the stack X times X over T. So T times X in Bernstein lengths. But okay, so that's the setup, and it is a monoidal category. We would like to have an analog of H tilde in this setup. But the naive hope, you just still use global sections, it's going to give you nothing. Because these sheaves, if L is non-trivial, the local, the global sections are all 0. So if we want to define analog of H tilde, we have to for something else. So let's recap the H tilde. The G mod B situation is taking global sections. which can be thought of as our harm from the constant sheaf. So now I work with these L monodromic sheaves. And so that means if I still put a constant sheaf here, because they sort of belong, they have different monodromy, they never talk to each other. This harm is always 0. That suggests we have to replace this constant sheaf by some object in this category. So one guiding principle for when we search for such object is the Hecke eigenproperty. So in the case of constant sheaf, on G mod B, or even G mod B mod U. So let's look at the action of mod B by convolution on right. No matter how you which sheaf you put here, when you act on the constant sheaf, you still get a copy of constant sheaf. That's the in other words, if I look at the subcategory generated by constant sheaf, shifts, this is stable under action. Which on the right. So that's that's a property which is used a lot in establishing the zorgo structure theorem. To define a functor, we can put anything here, but to put good properties about it, this kind of eigen. So in this situation, it turns out the eigen, there is there's analog of this constant sheaf. Sorry. So, analog of C in this kind of L situation. Roughly speaking, this is I mean, it's quite naive. So it's just the largest IC sheaf. In that category. There's a little subtlety here, which is there may not exist a unique largest IC sheaf. So this category, first of all, can be decomposed in general. It has a direct sum decomposition indexed by blocks beta. So it's really direct sum decomposition as a BG category. No harm or X between from different blocks. And how is this how to index these blocks? So we have this local system on the T, and under the while group action, look at its stabilizer subgroup of Weyl group. And this is in general not Coxeter group anymore. There's a canonical way of defining Coxeter subgroup, normal subgroup. This is Coxeter group. And this quotient, this indexes Cox. So let's take an example. L2 and take L to have order 2. L squared is trivial, but L itself is not trivial. There's unique such L. In this case, it's easy to write down some objects in our category. So we have G mod B mod B. There are 2 strata. On the unit stratum, have just a standard sheaf on the unit stratum, and then there was standard sheaf on the open stratum. So, but it turns out these two, first of all, these two, this of course is just extension are in a closed orbit, but this one is also plane extension. No way of that these two can interact with each other. This category actually decomposes into 2 blocks. Just direct sums of delta 1, direct sums of shifts of S. In this case, so L is order 2. There's a unique such order 2L. So the stabilizer under the Weyl group is the whole thing. But the circle part of the stabilizer is trivial. And so the group controlling the blocks is W. Okay, but you can ignore this if G has connected center. Then only one block. Only one block. And in that case, there is a unique largest IC sheaf corresponding to the longest element. So largest IC sheaf is the IC from IC on the W, which is the longest element in WL circle. I see on that sugar variety. So this carries a canonical set of simple reflections. Simple reflections here are not simple reflections of original object. That's the在讲课。So, that if we work with a single block, we restrict to a fixed block, we consider this functor of x from this what I see of W beta. So this W beta is the longest response to the longest element in the beta block. When beta is the unit element here, longest element in this Coxeter group, general, it's this longest element multiplied with some. And this still goes to, so what this goes to the Zorgo bimodules for the group. Sorry, it's not yet Zorgo bimodules, but to R bimodules. Rated R bimodules. This R is still the same ring here. So I'm not taking equivariant cohomology, but I'm taking the X between two objects in this category. That X still carries the module structure under this equivariant. The thing is that this functor is fully faithful on X sheet. And maps semi-simple complexes to Zorgo bimodules for this Coxeter group. So this was the built up on this result. We proved that this category can be related to similar Hecke category for a smaller group. Each block, let's just say for the neutral block, the beta equals identity. This is equivalent to usual covariant Hecke category for a smaller group. H is the endoscopic group for the pair G, and L, which is the same data as a semi-simple element in the dual group. From that pair, one can define a smaller. Which is not necessarily a subgroup. So this is not a causal duality statement. So this statement, both groups are on the same side, and I didn't have to put a mixed version on either side. So it's reasonable to expect that this functor can, the equivalence can in fact be realized geometrically, but we don't know how to do it. Proof still goes to Zorgo bimodules using that theorem. Also, the what's missing here is version of Victor's theorem that by purely geometric reasons, one can conclude that taking global sections is fully faithful on semi-simple complexes. We don't know what is a generalization of that thought in this monodromic setting. So the proof here is specific to the situation. Okay.
Have an example where it's really geometrically to construct geometry.
Well, When it's a subgroup, I think. So, for example, for generic L, H is just T.
Yeah.
Just, everything is concentrated on the unit coset. Restrict to that. I think if H is a subgroup, let's say Levy subgroup, then everything will just be concentrated on that Levy obvious equivalence. Otherwise, I don't have any example. Okay, so that's variant. Let me quickly mention. So, in the work of Bezrukavnikov and Dhillon, there's another variant where they consider symmetric subgroup acting on the flag right category. So here, again, one considers global sections. It's a little bit like the previous situation. This category can be decomposed into blocks. So this has a block decomposition. In particular, the constant sheaf here used to define this homology, this H functor, does not talk to all objects in this category. So the best this can work is in a principal block. Principal block meaning the block containing the constant sheaf. And what they prove is this is a similar Zorgo structure theorem. This functor is fully faithful on semi-simple complexes in the principal block. So this looks like maybe some general geometric machinery may apply. However, and there's no, so far as I know, there's no general machinery that guarantees this full faithfulness, even though you're still just taking the equivariant homology. The argument here is again specific to the situation. So both arguments are somehow. This argument is more involved. It involves implicit calculations for in the rank 1 situation. Okay, so these are somehow one can hope for some more general geometric reason, so that these results are special cases, but yeah, maybe probably don't have. Now let me talk about variants of this V tilde. It's again in the case of this real. So both this and this, they are modules under Hecke algebra. So let's consider here the monodromic unipotent monodromic, or the torus action on the right. So this will be a module for this completed Hecke category. So there's this Matsuki correspondence. Basically says if you work with G mod B on both on the right, you can replace K with GR. So this will form as a maximum compact, maxified maximum compact, you get K. And there's the Matsuki bijection between orbits. Order reversing, and there's a stronger statement says the category of sheaves are actually equivalent. But so in the work with Andrei Ionov, we developed a theory of tilting sheaves. In this situation, which I think is a kind of interesting because it's real algebraic situation. For example, we're not working with the usual notion of perverse sheaves. So here's a case of SL2 acting on the flat variety. So the orbit structure is two half spheres and now first we introduce a perversity function situation. So for each orbit, it's G1B. This is a GR orbit. So the perversity function is not just the well, for complex manifolds, we just take the complex dimension of the orbit. That's the perversity function. Here, of course, it's not, you take the real dimension divided by 2 to approximate the complex dimension. First of all, this is not always an integer. These dimensions don't always have the same parity with the real dimension. So real dimension 2, real dimension 1, real dimension 2. We need to make some adjustment to this perversity function. So it turns out the following definition is the right one. So you look at the image in G1U. Of course, that dimension is just a rank, twice the rank bigger than O. So yeah, so there's this action of T. This is the complex T. But this is a T torso. More complicated. Let me introduce this dimension. So I have an orbit, real orbit. So this can be identified with, so if I choose a point in this orbit, it corresponds to some Borel. So this is a homogeneous space of GR whose ordered Borel B of 1. So B of 1 represents a point in O. Stabilizer is this intersection. So this intersection determines a real form of the Cartan. So if you project the T, right? So every Borel, its reductive quotient is canonically identified. The universal Cartan And this gives a real form. The image here is real form. And the idea is, out of the naive real dimension of this orbit, we need to adjust it by how compact this real form is. So formula take the let's call this real form real O. We can talk about real points. So I take the real dimension orbit and I subtract by the dimension of the maximal compact. This basically is a product of S1s with R star. And you count how many copies of S1 that appear. It's real torus. Turns out this is always an even number. And at least when you go through all the orbits, they have the same parity. I think it's always an even number. So this is definition of the parity of the diversity function. Let's look at this example. The real dimension 2, 1, 2. Now, basically, to calculate this error term, I need to calculate the stabilizer of each orbit under the real group. But here, the stabilizer is SO2. So it's half plane. Stabilizer is SO2. Along the equator, this is the stabilizer is the split Borel is the Borel in the split Borel in SLR. So this is a compact torus. That means you have to subtract so this is not a the point is they have the same parity before dividing by 2. So this when I subtract, I get 2 minus 1. I adjust this dimension, then divide by 2. So this along the equator, this is the Borel, and it has split torus. So there's no compact part, just 1 minus 0. So the upshot is that I get the same number for all 3 orbits. So then, in this case, the notion of perverse sheaves, GR, SL2R acting on P1, is the usual sheaves because the perversity function is constant. It's the usual sheaves. So this is the ambient abelian category we work with by this perversity function. And define 3 monodromic total sheaves in this context. So this means if you restrict star or streak restrict of your sheaf, you always get the most free copies of most free local systems in degree negative. So how many free kind of monodromy operators you have depends on the orbit. So for example, on these two open orbits, you don't have any room for monodromy. So there's no monodromy is trivial. But along this circle, it's a circle on G mod B. When you go to G mod U, it's actually you get another circle, but you also need to remember that there is the SL2R equivariance imposed left. So here you're allowed to have one variable free monodromy. So this guy is actually how many dimensions you lose when you try to get the most free monodromic local system. This is the gap between maximal free monodromic local system and the actual rank of T. Okay, so the subtlety here is kind of freeness varies orbit to orbit, but there's this definition and all the usual properties of free monodromic tilting sheaves in the usual Hecke category actually also hold in this situation. In particular, one property is the when you act by this Hecke category, you start with a free monodromic tilting sheaf here, act on it by a free monodromic tilting. You still get a direct sum of free monodromic tilting. Stable under evolution by free monodromic tilting in the Hecke category. So example of such a free monodromic tilting sheaf. So here, what we can do is we start with constant sheaf. So I can't really draw the picture in G mod U. Let me just represent a sheaf here by some linear algebra data. Right? So for the usual sheaves, you can represent it by a quiver diagram where you have a vector space attached to each stratum, and you have an arrow. If you go from this exit path arrow, you go from smaller stratum to bigger. So here, the free monodromic guys, you put the free monodromy here. You put this power series ring corresponding to the equator, and put one-dimensional vector space on the upper hemisphere. This is the reduction. That gives a free monodromic tilting sheaf supported on the upper hemisphere. Similarly, you have one for the lower hemisphere. And you also have the one just concentrated on the equators. Those are the free monodromic tilting sheaves. Every such thing is a direct sum of indecomposables. Decomposables are connection with it's not just orbits. In this real group story, you have orbit and the local system. So GR equivariant local system on the orbit. This is slightly more complicated than G mod B mod B. And this is the reason we have block decom. Okay, So now, what is the Zorgo functor? Turns out the same idea, the micro-local idea of defining Zorgo functor for Hecke categories works here. Provided we have we make the assumption that the G is quasi-split. When G is quasi-split, we have a closed orbit. There's always a unique closed orbit. That's the flag variety. So flag variety of this real points of the flag variety inside this closed orbit. But in the quasi-split case, this really is half-dimensional in here, real form. Ready? And then we take microstock. In the generic codirection along the closed orbit. I mean, one can do this general, but what the quasi-splitness what it gives us is that this if we look at union of conormals, so these O are runs over GR orbits. So of course this is a subset and a T star G mod B maps to the new home. And this image hits a regular orbit. Regular nilpotent. This happens if and only this part is split. And this is really what the property we need. As to this microlocal picture, we want this covector to hit when you map it to the algebra, totally algebra. It's a regular nilpotent. Whenever you have a situation, so this is a kind of a meta theorem, is whenever you have a situation where you have a Hecke module coming from geometry, whenever the cotangent bundle hits the regular nilpotent orbit, take the microstock in that codirection, this is giving you a nice functor. In all the examples I worked with, it's actually a Zorgo functor. You can prove Zorgo structures clearly. Okay, so this is the Zorgo functor and the theorem. Okay. Taking this microstock, a priori is just a vector space. And in the case of Hecke category, we upgraded it to a bimodule over a certain power series ring. Here, this Zorgo functor can be upgraded to something similar, but this is less obvious to see. So modules over functions on something's complicated. So what's happening here? This is some affine variety, and I'm taking its coordinate ring. Maybe complete. Sorry. Monodromic. This part, H star, when you take the completed coordinate ring, it's just power series in H. That's the usual monodromy on the right. That part is easy. This part is less clear. What is A? So A is the algebra of the maximal split torus. Dimension is the real rank of this real group. On that, there's the real version of the wild group acting. Everything here is well defined, but it's not so clear where this symmetry comes from. It turns out this thing also part of the center of the category here. But we also don't know how to see it directly. There's not enough room. Monodromy consideration, the left doesn't give you that. So that eventually argue that this lies in this acts on the identity functor category. It's a kind of ad hoc argument. But anyway, you need this copy to state the structure theorem. So under this setup, Soda is fully faithful on free monodromic totals. So it's full analog of the zorgo structure theorem in the case of quasi-split real group. Oh, and also this functor is compatible with Hecke action. Acts by right convolution here. Zorgo by modules act by tensoring. That's all compatible. Yeah, so using this and coupled with the equivariant version proved by Bezrukavnikov and Dhillon, we can prove a Zorgo duality statement for real groups, for quasi-split real groups. So that was already proved by Bezrukavnikov and Dhillon. They didn't use a geometric argument for this monodromic side. For one side, they use a geometric argument. The other side, they use category O, more algebraic argument. But now we have also have a geometric argument parallel to the
Actually,
no, but feel free to go. I think I'm talking too much already. Yeah, thank you for your attention.
I missed it. So in particular, did you say that the G of R category is equivalent or something to A?
Yes.
It was
This was already in Bezrukavnikov,
But do you relate K with G of R or categories without any duality? Like
The-
Matsuki correspondence.
Matsuki is
This is known. So this is.
Matsuki is no, Matsuki
I
is on the
see.
one
Okay.
same side.
I see.
So it was Vogan or Zorgo duality is relating this.
Yeah, with something else. Yeah.
Well, you can either put GR here or K here.
Mhm,
right?
I see.
On this side, you put K. And Vogan gave the recipe how these real forms correspond to each other. So that for the split cases. This again, you need to mix it. Okay, so this is a kind of, you just artificially make a mixed version. This is the real thing. Or equivalent in the same, I mean, you need some decorations, but what's literally known is the principal block here, and here it's also some kind of principal block. Oh, well, no, so this is some block. So here you can. You start with a quasi-split group. This category decomposes into several blocks. For each block, Vogan tells you how to find a real form. This real form will depend on the block. For each block, you are comparing this block and always the principal block of the real side. This is a theorem. Dhillon. Matsuki is on the G side, relating. So you don't change the group, you just change K to GR. So this is a kind of a radon transform from bigger orbits to smaller.
Oh, the right hand.
Yes. So this equivalence is a combinatorial equivalence. Both sides are identified with some kind of zorgo bimodules. The one side is for this checks. The other side is this.
Those two rings are small.
Rings are isomorphic. You can see this way of presenting. Imagine this is matching with the K mod G mod B.
What do you credit to? Lies on yours.
Right?
Like if you give credit to, it relies on yours.
But it doesn't. So we gave a new proof
Oh,
of Zorgo structure theorem for one side of the equivalence, making the whole argument purely geometric. Their original proof, basically they treat this side as some category O, using algebraic arguments.
In your setting with Lusztig, is there a causal duality?
Yes, there is also a causal duality.
And what happens with the local system?
Oh, so sorry, I shouldn't say there's a causal duality because, as you said, it's not very natural to match local system on both sides. What I mean is, if you work with the monodromic version of this, there is a parallel Zorgo story. So okay, so now you can work with GU, but L monodromic on both sides. And this will have a zorgo functor, the analog of V. This is defined. This I didn't have time to explain. This in the affine case, this is related to the Klosterman sheaf that I worked with Chow and Ionov. So in this case, the statement is that this category can also be described using zorgo bimodules, using this functor. I don't have a canonical way of matching something for G and something for G dual, but eventually all these categories are controlled by just this combinatorial data. All you need is some Coxeter group, some kind of extended Coxeter group acting on some polynomial ring, or act with some reflection representation. You can have different groups, different local systems, giving rise to the same triples. But as long as those triples match, the categories will be equivalent.
Any more questions or from Zoom? Well, let's thank our speaker again.